Okay, class, let's see, this is the second video lecture, right? We're still pursuing antennas. And so all of these notes are again online and available. So I'm just basically walking through these notes, right? So the last thing we looked at was the freeze transmission equation, and there's an example there and a homework assignment for that. So hopefully you're having an opportunity to pursue that. And again, hopefully everyone is well. Okay, so right, there's all sorts of different types of antennas. I mean, the list goes on and on. But one interesting antenna is the patch antenna, right? Part of the advantage of the microstrip patch is it's low profile, so it's often used in cell phones, right? Or on a missile, for example, where the antenna can't really protrude from the exterior parts of the missile because of the speed of the missile would rip the antenna off, right? So these are so-called conformal antennas, right? That conform uh, to the surface, or in this case, conform to the cell phone. It's low profile, and so that's one of their advantages. Uh, so this material is really taken from Stutson and Field's antenna theory and design, right? We offer the antenna theory and design class in the spring. So it's currently going on with with our Fields 2 class. Right. So this is low profile antennas and personal communication antennas. Okay. So the microstrip patch antenna is shown here, right? Let's take a look at this real quickly. Right. So here's the patch, right? It's conducting, and the ground plane is conducting, and then the patch and the ground plane are separated by a dielectric block here, and the substrate dielectric constant is epsilon sub relative, epsilon sub r, right? So epsilon for the substrate would be epsilon naught times epsilon relative. However, most of the equations are in terms of epsilon relative. Okay, so the patch has some length L and width W, and the coordinate system is X, Y, Z up. Okay, and importantly, the thickness of the slab is T. Okay, so all these things are easy to see, uh, both here in the video and on the online notes that are up on the engineering FTP now, right? So we're going to feed the patch. There's different ways to feed the patch, but this is a microstrip feed, right? So here's your microstrip transmission line that's centered with respect to W on the uh, negative X side of this patch, right? So it launches a wave onto the patch. The wave propagates between the conducting patch and the ground plane, right? So this is just an extended transmission line. At least that's one way of looking at it, right? And over here on this side, it's terminated in an open circuit, right? There's no, now one could short circuit that in certain circumstances that would be appropriate, but in this case, it's open circuited, right? So this next plot down here, B, right, side view showing the electric fields, right? So here's the electric fields under the patch, right? And so the patch is typically, right, the way we design this thing is the patch is resonant. And so this length L is approximately a half wavelength in the dielectric. Okay? So we can fast forward down to this equation, and it shows that the length L should be 49% or approximately half the wavelength in the dielectric, or 49.49 times lambda. The wavelength in the dielectric is the wavelength in air divided by, right, the square root of the relative permittivity. So the wavelength in the dielectric shrinks inversely proportional to the square root of the relative permittivity of the dielectric substrate. Okay, so that's important to know. All right, so right, looking from above, right, you can see how the electric field looks, right? So the forward and back traveling wave are adding, right, in phase at the open circuit for the electric field and for the voltage for that matter. And so as you move away, you get a E field minimum or a voltage minimum at the center of the patch, and then another maximum on this side, right? Uh, and then there's a flip, right? There's a flip in the sign because this point and this point are half wavelength separated. And so you see that the fringing fields are in the same direction, right? So these fringing fields above the patch along this edge and this edge are what we call the radiating fields, right? So these electric field lines shown here, those are the fields that are responsible for radiating into space. These edges along here, right, on this side and this side, are what we refer to as non-radiating edges. So they don't radiate any field into above the patch, right? Uh, for all intents and purposes, right, the theory sort of assumes that this ground plane or assumes that this ground plane is infinite. And so for our purposes, we don't expect any fields underneath the ground plane. Now they will be primarily, the radiated fields will primarily be in the upper half space, right? And they will roll off and be attenuated underneath in sort of a, as we'll see in a minute, sort of a cardioid pattern, right? Cardioid pattern would be something broad up here, and then underneath it would roll to a zero as you went around the edge. Okay, so right, so radiating edge, non-radiating edge, non-radiating edge, and then we're feeding from the left, and so the wave propagates, hits the end of the patch, and reflects back, and then the patch length lambda over 2 is such that the antenna is resonant, meaning that the voltage and current uh, at the feed point are in phase, right? Now, the ratio of the voltage to the current at the input will give you the input impedance, right? Well, the input impedance is important to us, right? Because ideally, we'd want that to be the same as the characteristic impedance of the transmission line feeding the patch, right? Because that would ensure that there's no reflections and all the incident power is fed into the patch and then radiated into space. Right? There's some losses associated with the dielectric and the currents that are flowing on this finitely conducting substrate patch and substrate and patch. And so those will lower the efficiency, radiation efficiency of the patch, and that needs to be taken into account. Okay, so right, that's the general concept. Now, uh, we can feed the patch with a probe feed also, right? That would look something like this, real quick. Here's the looking from the side view. Here's your coax, right, from below, and the center conductor comes up, and you would drill a little hole, and then the center conductor would come up, and you literally solder that to the patch, uh, to the upper side of the patch, right? So this is the substrate, right? Epsilon relative. This is the ground plane. This is the patch, and so right, this is your coax, and this is the center conductor coming up. So you extended the coax center conductor up here. You drilled a little hole. You might have twisted this over and then put a blob of solder. So now you're feeding the patch. This is a so-called probe-fed patch, and you've moved the feed point over some distance, delta x, from the edge. Okay, so we're going to look at that in a minute. Over here, this shows a microstrip patch feed. This is a probe feed, right? There's different types of feeds, okay? And they have different design characteristics, pros and cons, and we'll talk about that a little bit, right? Okay, so right, design equations. How do you design one of these things? Well, pretty straightforward. You just make sure that, as I mentioned earlier, the length of the patch is a half wavelength or 49.49 wavelengths in the dielectric are 0.49 lambda divided by the square root of epsilon relative, right? So lambda is c, the speed of light, right? Because that's the free space wavelength divided by frequency. And so you can, so that puts frequency into the equation. And so if you know your operating frequency, then you can determine the length necessary for for the patch to resonate at that frequency. And we'll do an example pretty soon, right? Design of patch antennas is quite straightforward, but it's just interesting to see how this works, right? So don't forget, right? This edge and this edge are the radiating edges. It's the electric field along this gap right here that is responsible for radiating energy into space. Not only on this side, but that side as well. And again, these sides don't radiate. It's just this side and this side. Okay. And so one thing we might mention quickly, the standard patch, right, typically doesn't have that much bandwidth. Okay. So that just means that acceptable operation is can only be carried out over a small percentage of the center of the operating frequency, right? So if this patch is supposed to operate at 1 gig, right, you wouldn't expect you would expect less than 10% or less than 100 megahertz of bandwidth. What do we mean by bandwidth? It's the range of frequencies over which this thing can operate so that the standing wave ratio on the feed line is less than or equal to 2, right? So we say the bandwidth is predicated on a 2-to-1 VSWR. So it's the range of frequencies over which the standing wave ratio on the feed line is equal to or less than 2-to-1, right? So at resonance, at match, it's 1-to-1. And then as you move up higher in frequency and lower in frequency, the standing wave ratio degrades, and the range, the bandwidth is defined as that range of frequencies over which the SWR does not exceed 2-to-1. Okay, so that's a typical definition. Other definitions are used, right, depending on circumstances. Right? And so this formula is pretty good, right? It's just a quick back of the envelope like formula. And so this thing degrades, right, if the patch becomes too thick. So the patch is typically a small fraction of a wavelength thick, right? And it also, the formula degrades as well for high dielectric constants, for the substrate being a high dielectric constant. Well, why would you want a high dielectric constant? Well, the nice thing about that is it's going to shrink the length, right? As epsilon relative goes up, the required length for a given operating frequency is going to be smaller and smaller. Right, that's the good news. The bad news is that the bandwidth deteriorates, right, and this simple equation is not as accurate either. So the design becomes a little more cut and dry. Okay, right. So let's move on to the next page of notes, right? So here, there's more accurate formulas, right? This is the one we'll use by and large, right? This little simple formula for the half wave patch. There are other formulas, right? So this is one where the length is 0.5 lambda over the square root of epsilon relative, right? So half a wavelength in the dielectric, and then minus this so-called fringing distance, right? So what does the fringing distance take into account? Well, you see how these fields come out here. So the actual electrical length of the patch depends on the amount of fringing that occurs, which obviously depends on the substrate thickness as well. Okay, so it's just half a wavelength in the dielectric minus 2 delta L, and then this is the fringing length, and then we have a formula, and this is probably empirically derived, meaning they measured a bunch of them and then they fit this formula to the measured data. And it depends on width and thickness, right? Width of the patch and patch, as well as this effective dielectric constant, which depends on the thickness and the width and the actual relative dielectric constant of the patch. Okay, so right, another formula, one that's a good bit more accurate. Right. So this total fringing length due to fringing of both edges, right? Delta L for one edge, delta L for the other edge, so it's 2 delta L. The amount of patch length should be reduced below a half wavelength to achieve resonance. So this is the amount that you need to reduce the patch below ordinary half wave resonance, right? The simple formula just took care of this by replacing 0.5 with 0.49. This is obviously more accurate, but also more cumbersome. Of course, you could put it in a little MATLAB program and compute it quite straightforwardly, or in your calculator for that matter. Okay, so right, this again, the patch is going to radiate primarily above uh, the patch, above the ground plane, right? So it's going to radiate in the positive z space, right? Those ranges of angles in a spherical coordinate system from 0, right, to pi over 2 and phi from 0 to 2 pi. So that's the upper hemisphere. Okay, so if you go through the theory, and we could do that, and we may end up looking at that again in the case where we have see, this thing can be analyzed as an array. So we're going to talk about arrays later on. So the far field pattern can be easily understood in terms of line sources. This is a line source, and this is a line source. So that is a pair of line sources, which generates an array, a simple array. So you can use array theory to predict the radiation pattern, right? So we may end up doing that, but for now we're just going to take these formulas as given, right? So, right, the E plane. So we have an E plane pattern and we have an H plane pattern. The E plane is the phi equals 0 cut. The H plane is the phi equal 90-degree cut. Right? Why is that? Let's back over here, right? The electric field is along this direction, and so in the XZ plane, right, the electric field lies in that plane. So we call the XZ plane pattern the E plane cut, and then the magnetic field is orthogonal, right? And so we call the YZ cut the H plane cut. So E plane cut, H plane cut. E plane cut is the phi equals 0-degree measurement. The phi equal 90-degree plane measurement is the H plane measurement. Okay, so this is so in the H plane, it's basically a sinc function, right? That depends on W, right? And in the E plane, it's a dipole, a dipole looking pattern uh, that's shown here, right? So beta, right, is 2 pi over lambda, free space, phase constant. L is the length of the patch. So the E plane pattern is controlled by the length of the patch. The H plane pattern is controlled by the width of the patch. So that's something interesting to observe, which makes sense, right? Along the E plane, it's the length that controls the pattern. Along the H plane, it's the width that controls the pattern. Okay, so these could easily be put into MATLAB and plotted, or you could literally do it by hand for that matter. Okay, right. What else is of importance to it, right? Well, we're going to want to know what the input impedance uh, is looking into the path. So the input impedance at the edge of a resonant patch ranges somewhere between 100 and 400 ohms, typically, right? And so we have a simple formula for the input impedance of a resonant patch, 90 times the ratio of epsilon relative squared to epsilon relative minus 1, length over width quantity squared. Okay. So we're going to work with this formula in just a second through a simple example. And then this shows, right, the bandwidth, right, the bandwidth of the patch. Again, the range of frequencies over which the input impedance is such that the standing wave ratio on the feed line is less than or equal to 2 to 1. Okay. All that transmission line theory coming back, and you have to remember what that's about now. So, right, 3.77 epsilon relative minus 1 epsilon relative squared, width divided by length. And so the bandwidth is T over lambda, right? So, right, real skinny patches have small bandwidth. As you increase the thickness of the patch, the bandwidth increases. But then remember, the simple formulas above are less accurate. So thick patches have more bandwidth than thin patches, but the thin patch adheres to the formulas, and so maybe it's a little easier to design based on formulas. Right? There are more sophisticated ways of solving this problem via numerical methods. Okay, let's move on a little bit. Right, here we go. So let's plot. Let's see what here's a typical input impedance characteristic of a patch antenna, right? So here we're plotting the input resistance versus frequency for some patch, and then we're also plotting the input. I misspoke. This is input reactance as a function of frequency for a particular patch, and this is the input resistance as a function of frequency for a particular patch, right? So what do we mean by resonance, right? Well, resonance is that point where the reactance goes to zero, right? Here it's positive, right? And so that's inductive reactance, and then here it's negative, so that's capacitive reactive, right? And so in between it's zero, so this is the frequency at which the patch resonates, right? So then we want to know what is the real part of the input impedance at resonance, or at where the point at the frequency where the reactance goes through zero. So this is plotting input resistance versus frequency. So you can see, at about 3 gig, it comes up. It's a couple of hundred ohms, right? So we said somewhere between 100 and 400 ohms. So that's about right. And he shows different methods, right? Measurement, that's the most accurate. And then there's the simple model that we're using. It misses it a little bit. That's this dash curve. And then more sophisticated numerical techniques track the measured data quite accurately. Okay, so then, right, we move down. And so now we take a look at the radiation pattern, right? The radiation pattern. So we're going to look at the E plane and the H plane, right? So here's your E plane pattern. Right now, as you go down, this is going to roll off and be small on the underside of the patch, right? So it's a pretty broad pattern, right? It's a fairly broad pattern. And then here's your H-plane pattern. Notice that the H-plane pattern goes to zero at theta equals pi over 2, or in the plane of the patch. And so, those are the little formulas that we had. It was a solid line, and then the dots are the measured data. So it tracks pretty good. Not really great, but the theory, right, these formulas give a reasonable representation of the pattern, right? So don't forget E plane and H plane, right? Now, if we know the E plane half power beam width, can't speak, and the H plane half power beam width, then we should be able to estimate the directivity, right? And if we know the efficiency, then we can estimate the gain. So we're going to we're going to do that in a minute. So just remember that from our previous general discussion on antenna theory. All right. So page 3. Move to page 4. Here we go. So let's take a look at different kinds of feeds, right? So as I mentioned earlier, right, here's a probe feed, right? Here's a probe feed. And so here, right, we're moving the probe in a length delta X from the edge, right? So this is a coax down here. Uh, right. The other thing we can do is here is one length of transmission line. Here is another. Here's your standard transmission line. Maybe this is, who knows, maybe that's 50 ohms, right? Maybe looking into the patch is 100 ohms. I don't know. I'm just making this up. And so we could use a quarter wave transformer, right? This length from here to here would be lambda over 4. Recall quarter wave transformers from T-line theory. And so we'd need to make the characteristic impedance and thus the width of this transmission line here would have to accommodate the adjusted rather so that the characteristic impedance of that section would be what 50 square root of 50 times 100, or the geometric mean between the input impedance to the patch and the impedance of the feed line. Right, so we could match it that way using a quarter wave transformer, or here's another way, right? We could cut a little notch out of it and feed it that way. And that's again, the notch would be a delta X thick. Okay. So you can also, right, you don't even have to you don't even have to solder the center conductor to the patch, right? You can feed this with so-called proximity feed, right? It doesn't actually touch, but it couples electromagnetically, right? You're at high frequencies now, so it's not like circuit theory. That's not an open circuit, right? That thing actually couples into the patch. Because why? Because the dimensions of the circuit are on the order of a wavelength. We talked about that. Whenever dimensions of the circuit become on the order of a wavelength, field theory has to be used to predict performance. You can no longer use simple circuit theory. Right? Here's another edge fed gap, and then this just comes underneath and it doesn't touch, right? So this is another so-called proximity feed. So here's your patch. Here's another layer of conductor. That's insulator. This is insulator, and then the feed comes down here. And so that gives you more parameters to adjust, and consequently, you can increase the bandwidth of these things by using some of these other feed methods, right? So that's an interesting possibility. So what is the input impedance in this case? Well, it's the input impedance that we computed previously for the edge fed, right, times cosine squared delta x of p over L, right? Cosine squared. Wait a minute. I think there's a pi missing from this. Let me fast forward. Always little errors you have to correct. Kind of a lull in the action here. Sorry. Yes, that's an error. There needs to be a pi in here. Pi delta xp over L. Cosine squared pi quantity pi times delta xp divided by L. Okay, little error. Be careful. Error in notes. Okay, so again, though, what's the issue? The issue is what is the input impedance when the probe is moved over, right? And you're feeding not at the edge, but into the patch of distance delta x of p. It's the input impedance that you would see if you fed it at the edge, this number times cosine squared pi delta x of p over L. So we say the input impedance changes like the square, cosine squared of this quantity. Okay, right. Because we may want this. This is not 50, and we want the input impedance to be 50 ohms. So then we can figure out how the probe, right? And also, why does that happen, right? Why does it change as you go back? Go back to this, right? Here's our voltage, if you will, as a function of position. The current distribution is going to be like this, right? Because it's a standing wave in there. So wherever the voltage is a minimum, the current's a maximum. Wherever the voltage is a max, the current is a min, right? This is, for all intents and purposes, an open circuit. So you know the current there is zero. This is the middle, this is a quarter wavelength away from uh, an open circuit, so the current's going to be maximum there. So as you move that probe in and out of here along this, you're changing the ratio of the voltage standing wave to the current standing wave, and therefore you're changing the input impedance. Right? So that's what we're doing while we're moving this probe in, right? We're changing the ratio of voltage to current. Okay, page 4. Just keep pushing here a little bit, get through these notes. 1, 2, 3, 4. Oh, down here, right? Before we pursue this concept a little further, right? Here's some interesting designs for creating circular polarization, right? How do you create circular polarization? Well, you need an electric field in the x direction, you need an electric field in the y direction, and so this needs to be a radiating edge, and that needs to be a radiating edge, right? So you need to excite fields running this way and that way. In addition, they need a 90-degree phase shift, right? So circular polarization is created with two orthogonal components of field and a 90-degree phase shift between them. So say that CP is generated by both space and time orthogonality. Okay, space and time orthogonality, or it's orthogonal in both space and time. So here's some different ways you can feed it at the corner, right? You can feed it here and put a slot in there that interrupts the fields and sends some of them this way and some that way, right? You can slice the edge off, and you can put a shorting. You can put a little. You could have a probe feed that's offset from the center. Right? It'll excite a field this way and this way. Distance between here and here is different than that, and so that's how you get the 90-degree phase shift. So patches can radiate CP. Now, the standard patch that we were discussing earlier is a linearly, the radiated field is linearly polarized, right? So these patches can radiate circular polarization. What's the good thing about circular polarization, right? No matter how, if you have a linear receive antenna, no matter how it's oriented with respect to the patch, you still get the signal. Okay, so that's becomes important in satellite communications when the satellite is tumbling around and you want to speak to it, right? You want to talk to it. So you need to be able to we need to use CP, otherwise you won't be able to stabilize the satellite. Okay, so we talked about those kinds of things. And this next view graph shows a more sophisticated design, right? Look, multiple layers, right? Uh, multiple layers, patch, substrate, another patch, substrate, feed, the gap, right? These gives you lots of different variables to adjust to increase the bandwidth, right? So this is an aperture coupled stacked patch, right? And the intent here is to increase the bandwidth or for broadband operation, right? So patches are also often used, right? Very often used in arrays, right? Patch, 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 patch. Right. So this is a 4 element. This is 1, 2, 3, 4 times 4. This is a 16 element, right? So you're feeding this four uh, four patch array, Right. We're going to talk about arrays coming up. Do a little bit with arrays, and that'll be the end of this material. And we'll try to quiz out on this in the not too distant future. So keep up with this stuff. Right, 4 patches. Right. So this is a 50 ohm line. Right? So we want the input impedance here to be 50 ohms. Right. So right, if this is if that needs to be 50 ohms, looking that way and looking that way needs to be 100 ohms. Right. If that's the case, then looking that way and looking that way needs to be 200 ohms. Right. So looking into the patch needs to be 200 ohms. So we need to adjust the width and length in such a way so that the input impedance here is 200 ohms. So if I see 200 in here and I see 200 in here, then at this point I see 200 in parallel with 200 or 100, right? And so I have a 100 ohm characteristic impedance transmission line here, and so it's properly terminated. Ditto down here. So I see 100 looking that way, 100 ohms looking this way, 100 in parallel with 100 is 50, and so that matches up to the feed line here at this location. Okay. So if I want 50 looking into C, then I need to see 200 looking into each of the patches. 200 in parallel with 200 is 100. 200 in parallel with 200 is 100. 100 in parallel with 100 is 50. Everything's matched up. Okay. So because these line lengths are the same, right, all of these patches are fed in phase. And so you're going to have a main beam maximum broadside to the plane of the page, right? The main beam maximum is going to be in the Z direction. And then we're going to get some gain, right? Because we've increased the effective electrical size of this antenna. That's the reason we use arrays to up the gain, right? So the pattern of the array is going to be narrower, right, than the pattern of one of the patches. So we get a multiplicative factor here. So we make the half power beam width skinnier, smaller, and so we know the directivity is inversely proportional to the half power beam width squared, and so the directivity is going to go up, right? It'll go up even more here, right? Because you got this repeated 4 times. 1, 2, 3, 4. Okay, arrays. You can kind of begin to think about arrays a little bit. We're going to talk about those more and present some general theory next week. All right. I think there's a blank page in the notes. So this one's blank. Also in the notes. It crept in on me. Okay. Right. Let's cut to the chase here and do an example. Let's apply some of these simple design formulas for a patch antenna. Okay. Once we finish this, that'll get to the end of these notes. Right. So we have a probe fed rectangular patch. It's 0.127 centimeters thick, right? It's almost 14 centimeters long and 20.45 centimeters wide. Okay, so the dimensions, thickness of the patch is defined, the width, the length, thickness, length, uh, width, and the dielectric substrate. The dielectric constant of the substrate is also defined and given as 2.54. So calculate the resonant patch length at 660 megahertz using the simple formula that we have, right? So we want this thing to resonate at about a half a gig or 660 megahertz. So, and then in the B part, calculate the input impedance for an edge fed, and then calculate the input impedance for a probe fed that's 4.485 centimeters from the edge. Draw the patch, draw the design, draw the top view of the patch indicating the probe feed position, and then calculate the bandwidth of this thing. Right. So we're going to use the simple formula. So we need the length to be 49% of the wavelength in the dielectric, right? So that's going to be 0.49 times the wavelength in free space divided by the square root of epsilon relative, right? So we're going to replace the wavelength with the velocity of light divided by the frequency. And so we've got everything now. 0.49 c is the speed of light. The frequency that we want this thing to resonate is 660 megahertz times 10 to the 6, and then square root of the permittivity, 2.54. And so that gives us a length of 13.97 centimeters, which agrees with the given length. So by making this thing 13.97 centimeters long with a substrate of 2.54, epsilon relative of 2.54, we know it's going to resonate at 660 megahertz. Right? Pretty low frequency, but it's just an example. All right, let's compute the input impedance, right? If we're feeding it at the edge, right? And this is the formula for the input impedance at feeding it at the edge, right? The probe comes up and just touches the edge, or the transmission line comes up and connects to the edge of the patch. Okay, 90 epsilon relative squared over epsilon relative minus 1 times length over width squared. 90, 2.54 squared, 2.54 minus 1. It's 13.97 centimeters long and 20.45 centimeters wide. That was given. So that gives us 176 ohms. Right. So looking into our patch, we see 176 ohms. Okay. So then, right, in the C part, calculate the input impedance for a probe fed if the probe is moved over to 4.485 centimeters from the edge. Okay, so that is, I don't know why the problem that I took this from was somewhat screwed up, so I don't know why this is not correct. This should be 4.485, right? So correct this. Right? The video's right. The uploaded notes have a little error, so pay attention to that. So the input impedance, 4.485 centimeters from the left of the patch, is the input impedance at the edge of the patch times cosine squared pi times delta x, right? 4.485 divided by 13.97, which is the length, right? So I think if you do this right, be careful. This needs to be in radians in your calculator. You just put the numbers in like this. And so that turns out to be 50 ohms. So by moving the feed over 4.485 centimeters from the left of the patch, we're now able to get the input impedance to be 50 ohms. So it's matched to a 50 ohm transmission line, right? So we brought it down from 176 ohms to 50 ohms by moving the probe in. So in the D, draw the patch. So I've done that here. I guess I have to zoom out. Zoom out. So here's the patch. Build this up some. Right. You'll see this online. So this is to scale, 13.97 this way, 20.45 centimeters this way. So this is looking down from above, X, Y, radiation up, right, toward the camera lens, right. Here's the feed location in the center of the patch, right. Here's the center line. And we moved it 4.485 centimeters over. And so this is where the center conductor of the coax comes up. And so that's a blob of solder. Okay, so we're feeding it here. And then the input impedance that 50 ohm coax sees is 50 ohms. So it's matched at 660 megahertz. But what's the bandwidth, right? Over what range of frequencies is this thing going to behave reasonably well, right? So back to this sheet, right? The bandwidth is, zoom back in, the bandwidth is 3.77 epsilon L to the minus 1 over epsilon L squared W over L T over lambda. Put in the numbers, right? Here's the thickness, 0.127 centimeters, so 10 to the minus 2 meters, and then divided by lambda, which is speed of light divided by the operating frequency. That gives us 3.681 times 10 to the minus 3, or 0.368%. So, right, these things are it's not even 10%. So you have to do special things to get more bandwidth. So if I want the bandwidth in megahertz, I have to multiply this number by the operating frequency, which gives us 2.43 megahertz, right? So, right. So again, let's use this blank sheet. What's that going to look like when we talk about bandwidth, right? This is VSWR versus frequency. This is 660 megahertz, right? And the VSWR is 1 right there. It's matched. As you move off of that, right, the VSWR is going to increase. And so this is 2 to 1, 1, 2, right? Right. As you move up that way, it's less matched. And so this range right here is, what did we calculate? Memory's gone. 2.43 megahertz. 2.43 megahertz. Right. So this is the range of frequencies over which the VSWR on the feed line is equal to or less than 2 to 1. Okay, so pay attention to what that means. So if we were at the university, right, we could take this patch that we designed, feed it with a coax, connect it to the network analyzer, and this would be what we would measure. Right? It would operate right here, right? As you put your hand over the patch, like this, literally, while you measured it, this curve would jerk around, right? Because the interaction of your hand with the waves radiated by the patch would interact and change the input impedance. Okay? Something fun to do. Okay. All that. So you've got a pretty nice example now, right? So here's some homework for you, right? A probe fed square microstrip patch, right? Length is equal to width, 0.3 centimeter substrate. The relative dielectric constant of substrate is 4.53. Is designed to be, you want it to operate at 3.72 gig. Find the patch length at resonance, right? The length and the width will be same. You use a simple formula to find the length, right? 0.49 lambda divided by the square root of epsilon lambda. That's all you got to do. Find the probe location for 50 ohm input impedance, right? So it'll be very similar to the example we just worked, right? And then here, number 20, so a couple of little patch problems. Work these up, and then just as before, I'm going to publish a solution to this pretty quick. So you got a chance to work it first, and then when I publish the solution, you check your work against my work, and then send me an email verifying that you've done the problem correctly. Right. So we're backing off on the on this while we're having to operate this thing away from the university. So all you got to do is just compare your work to my work and tell me that you've done that, and I'll give you full credit for the problem. Okay. So number 19, number 20, commercial microstrip patch antenna has half power beam width in both principal planes of 100 degrees and a radiation efficiency of 70%. Calculate the gain in dB. See if you can work through that. Right. So how are you going to do that? The directivity is 4 pi divided by the beam solid angle. Beam solid angle is approximately the product of the half power beam widths in the two planes. So, right, half power beam width in each plane is 100 degrees. So express each of those in radians, multiply them together and divide them into 4 pi. That gives you the directivity, right? The gain is going to be 70% of the directivity, and then you got to turn that into dB. Straightforward. So the next and last topic that we'll discuss will be antenna arrays, right? You're going to see some material on that next week. Read the book, check the FTP site frequently. Right, again, these notes are out there. Right, here is the list. Right, right. Problems 14 through 17. Right, here's the names of the people that have verified to me that they've checked their work against mine. Right, I still need some more names. Right, so I think this is 23 students so far have, have let me know that they've done 14 through 17. There's more than 23 students in the class. Right, so try to email me early next week on this stuff if you haven't finished the 14 through 17. Right, and you've got some work to do on this patch antenna. So there's plenty to do here. Email me if you have a question or call me on the cell. Don't call after 10 o'clock. I go to bed at 10 o'clock. I wake up around 7. You can call me anytime in there. Okay, very good. That's the end of this.